Hello, everyone. My name is Sudarshan. You can call me Sean, and I'm here representing the team CogniChords. Before I start, I want to say that the other team with the name Cognicite, this was completely unintentional. So it was a very pleasant surprise that we had a very similar name. Moving on. Oops. Yeah. So our team was looking to help artists, DJs, and everyone else express their emotions through music. We were thinking about how we can create this emotional resonance between performer and art and their audience, just like one of the previous teams. But we're also thinking about how we can help autistic children communicate their emotions, or people who can't verbally communicate their emotions speak emotionally through music. And the way that we went about doing that, just a brief overview, we were one of the few teams that don't have access to that amazing gel headset. So we're using the OpenBCI Ultracortex headset, which is a dry electrode headset. We're detecting emotions from that, and then we were going to generate audio based on those emotions. And then from there, we were going to actually play the audio and to do all of that in real time as much as possible. So I'm just gonna start with a demo video just to, I think the demo video sort of speaks for itself. And I also want you guys to pay attention to the actual music, the beat. You'll notice that it changes adaptively as my emotional state changes. So let me go ahead and play it.
Now be happy. I'll try to be happy. Come on, just think my face. I know the big joke. Okay, now let's try to be sad. And happy again. Yeah, it works. How do you conjure emotions on demand?
I'm just imagining things. Thank you. Yeah. So basically, the way that we implemented it, it actually starts with two separate components. That's the emotion recognition side, and that's also the audio generation side. So for the emotion recognition side, we start with the BrainFlow API, which actually helps us pull EEG data off the serial port from the headset. And then we do some quite extensive feature extraction. We actually extract about 17 features for each of the 8 channels across a wide variety of stuff, from Hajar's parameters all the way to wavelet decomposition and EMD. We take those 17 features that we get, and then we use 3 KNN classifiers across the 3 emotional axes of sorts, the valence, arousal, and the dominance axes. We were very thankful and lucky that we actually got the Dreamer dataset before the hackathon started, and we had access to it, so we could use it to train our classifiers and then just fine tune a little bit on some individual data. So from the output, we will get 3 emotion scores. Those emotion scores range from 0 to 1. And now how we actually get that into audio is that we first do some prompt mapping. So we map these emotion scores into prompts, but we don't just map them into discrete prompts. We actually map them into a latent space between prompts. So to explain that, it's like if you have a sad and if you have a happy, and the score is somewhere in between, like 0.5, you can actually find the intermediate space in that latent space, and then sort of use that as the input to the next step. Directly goes into this refusion model, which another team already talked about. But just to summarize again, it's like stable diffusion, but instead of making images, it actually makes spectrograms. And you can take these spectrograms and you can regenerate the audio from them, and then you can play that audio in real time. So we managed to do all of this in real time because our program's quite fast. And then we actually added a little tidbit. We added a UI that allows you to, one, to customize the prompt, so you can change what valence represents and what arousal represents and the kind of music that comes out. And it also lets you get some feedback onto what the emotional state of you is. So you could see that in the video just now with the 3 bars that were going across the screen. The results were pretty good. Our KNN classifier was doing a 90% accuracy across 10-fold cross-validation. You'll see the confusion matrices across the 3 different scores and say it's pretty good. And then the interface screenshots, those are just some visuals from the application. It's actually a terminal interface that you would have seen in the video. And I think it did a really good job of allowing me to first figure out what kind of sounds actually sound good. by customizing the prompts, and also giving me some feedback on what I'm actually feeling, and I can sort of tune what I'm thinking based on that. Because the way it works is that I have to visualize a memory that is either very happy or very sad, and I sort of that helps me change that valence state. So in terms of reflection, I think data scarcity was a big challenge in not just emotion recognition, but throughout broader EEG problems. Just having enough data to be able to train a big enough classifier is a big issue. This is why we went for like a very simple classifier, because they perform better without overfitting. The second part is, I think definitely more time spent on fine-tuning the data would have been very useful. We did find that sometimes it wouldn't do exactly what you wanted. You'd have to like fight the system, or try to imagine really, really hard to get the values to change. And then the last one, I think we realized how important the hardware is, because we spent a lot of time finicking around with the EEG headset, the OpenBCI one. And because it's a dry electrode, it's quite challenging to get it to have good contact and not have the impedance, the skin impedance sort of affect your readings. And so reducing that noise and possibly adding more channels is definitely a direction in which we would take the project. And most importantly, all of us had lots and lots of fun trying to fiddle with all of these things. And we were working remotely, pseudo remotely, because one of our teammates is actually in Singapore. So yeah, this was us recording our final video, and we had a little virtual hacking space in Galatown where we would sit around a swimming pool and talk about what we were working on and work together. So these are just some group photos. These are references. We actually reference some papers on exactly how we did the valence and arousal classification. And yeah, that's it. Thank you so much.
Thank you very much for the nice presentation. And we have a question here.
Yes, it's really crazy what you did. Super cool. I was wondering, I'm assuming that you make an API call to the refusion to kind of get the spectrograms. How often do you make that API call, and how do you make sure that that fits kind of real-time music?
Yeah, so we actually do 5-second slices. So the features are computed every 5 seconds with 5 seconds of EEG data. Then we shoot that over to Refusion, and we have it running on a cluster remotely. And so that sort of, that takes about 2.5 seconds to process and give us the result. So we have 2.5 seconds of buffer in case the Refusion model doesn't get back in time and there's some network latency. So yeah, so it's 5-second windows, 2.5 seconds for Refusion to get back to us. So by the time we have still another 2.5 seconds before the next API call has to go up.
Yes, thank you so much.